You're on, Alex.
Hi, everybody. Welcome back to the Astro Imaging channel. If I sound a little goofy tonight, it's because, well, hi, Alex. This is Alex from the Astro Imaging channel. And I'm goofy. But it's also because I've spent the last 4 nights at nightfall and stayed up late observing visually. And I've had a really good time doing that. But we're back with the Astro Imaging channel team. All of those who were at Nightfall, we do appreciate you. All the nice comments you made about here, so we really appreciate that. Tonight, we have somebody coming to talk to us that is one of the most popular recommendations on cloudy nights. When somebody says, hey, where do I learn about this? How do I learn about to do that? Bob ZEQ, for instance, always mentions Charles, and so do a whole bunch of other people. So we're gonna hear from him. He's got some new stuff out, and I think we're all gonna enjoy hearing about that. But first, because it's traditional, we need to look at what's happening next week when Trevor Jones comes. He's astrophotographer at the Astro Backyard, and he's going to tell us about his evolution of the backyard astrophotographer. And I heard the bones of this presentation back at AIC last spring, and I think you guys will enjoy hearing from Trevor. He's got about 4 billion followers on his YouTube channel, and that's cool. John Talbot's coming up telling us a little bit about the latest generation of CMOS cameras after that. Molly, our very own Molly, took it upon herself. She saw the imaging rigs of Okie-Tex, and I was there with Larry, and we did some interviews with some people, and she says, oh God, I can do a lot better than that. And so Molly is going to come in, and she went to Okie-Tex, and she did some interviewing, and she's going to show us some amateur astrophotography rigs, and we're going to looking forward to that. And then one of us, again, the next week, Eric Coles is going to get together with Detlef and tell us about folded refractors. And then you're going to do some work, because the week after that, we're going over to the TAIC workshop. And the TAIC workshop, as you can see, is just a click away. When you get to TAIC workshops, that's where we give you a set of data and you tell us how you would like to process it. This particular set of data we're getting from one of our TAIC volunteers. Terry Robeson has sent us up something from south of the equator, NGC 55. A lot of really good data. You can go over and get the data by clicking on this link right here to get the zip file with all of his exposure data there. And then when you're finished processing, you send it in here, and Rory will contact you and talk about how you did it and what you want to tell the other people and things like that. Now, remember, these workshops go on a couple of times a year, and we have a number of them still available. And if you thumb through the rest of this website page, you'll be able to find all the other things there are to do. Once again, we are filled with really good presentations, everything except for the holidays, which we take off Christmas and New Year's. But we do need people to contact us and tell us that you would like to make a presentation. Now, you don't have to be famous like Charles Bracken or like Trevor Jones. You just have to have something that you've got, that you've done in astro imaging, that you would like to share with other people. And if you're smart enough to figure out how to plug in a camera and run PhD2, then you are smart enough to put on a presentation for the Astro Imaging channel. Believe me, it can be done. So contact us, hit the contact button, tell us who you are, and sign up. Okay, I think I've covered most of the announcements, so it's time for me to get over here and stop sharing and turn it over to our presenter for the night, Charles Bracken.
Hey guys, thanks so much for having me. It's great to be back. Yeah, really looking forward to showing you guys what I would like to think of, at least, as the widest wide field possible. So this is, let me switch over here to my presentation. All right, so I'm going to spoil the punchline just a little bit. This is the image we're going to talk about. So we're going to talk about this a lot. So this image that you see in front of you is the whole celestial sphere. in a single image. So we'll talk a little bit about this image, what you can see on it. I think it's cool just to get a sense, especially if you're new to astrophotography, or even if you're more advanced, to see what's out there and see the relative scale of things. So I want to talk about that a little bit. But also, I'll spend some time talking about how this image was acquired. So as you can see there, this took a couple of years. We took this at 3 different global sites. It's a massive mosaic of 153 panels, 7,000 subexposures, and the final image was about a gigapixel. So who am I? So if you don't know me, I'm Charlie Bracken. So one of the things I do is I write books on astrophotography, the Deep Sky Imaging Primer, Astrophotography Sky Atlas, Astrophotography Planner, and then a new book this spring, which I'll show you because it's where this image came from and what it was designed for. I'm in Bucks County, Pennsylvania, and like a lot of people, it's cloudy here all the time. Although I've had a good run the past couple of weeks, pretty excited. I had 3 clear nights in a row, which is unusual. Those people in Arizona are like, I don't see how that's special, but it's pretty special here in the East Coast. On the right, you see Max Whitby. Max couldn't be here today, but he's the one who acquired the data for all the images you're about to see. He's not here just because he's in the UK and it's 1 in the morning in the UK. But Max used to work for the BBC. He's published some books and some popular apps. But he also is in a cloudy spot. He's in Northumberland in the UK. And you can see in the back there, that's the North Sea. So it's very dark where Max is, but pretty cloudy as well. So this was an odyssey that required us to set up remote telescopes in a couple of different places around the world. So we'll get a little bit into what it took to do that. This, I just want to say, this is The Visible Universe. This is the book that came out this spring that Max and I co-authored. It's got, you know, all the best astrophotography targets and when to view them from where they're visible. And when Max and I put this book together, we wanted one image that we could show the whole sky and then show where all these different astrophotography targets are. So where are all the popular astrophotography targets that are in the sky? And so this is what it looks like in the book. This is the image we're going to talk about today. This is the whole sky, and you can see. So we'd, in homage to Messier, or at least the modern Messier catalog, we decided to pick 110 astrophotography targets, and that's why you see those numbers on there from 1 to 110. And these are kind of like the best variety pack of all the different things that are available to image in the sky. But this one image, we thought, oh, we'll figure out how to put that together later. And then we thought, this is actually going to be a pretty big undertaking. So let's have a look at the image in sort of a clearer view here. So this is the whole sky. I think it's really pretty just as an image on its own. Like, I think it's just nice to see the whole sky. It is in what's called equirectangular projection. It's similar to the Mercator projection. You might have a map that you've, you know, it's a typical map of the world where you get that distortion toward the poles. But it's a very convenient way to show everything, even if you sort of have to deal with a little bit of stretched out stars at the top and the bottom. We're going to go into a little bit of detail before we get into how this image was created. Let's just zoom in and have a look at some of the most popular areas in the sky and what they look like. I also think it's great that, you know, in the United States, we learned this is the Big Dipper. I understand it's the Plough in the UK, but it's just amazing how prominent that constellation is, that it just stands out right in the center of the image. Of course, you've got the plane of the Milky Way here, and many of the best astrophotography targets lie along this plane. If we look toward the center of our galaxy, if you're looking toward approximately Sagittarius, that would be this area here, right? You see the bulge there. That's the bulge of the core of our Milky Way. And if we zoom in there, just to give you a sense of the resolution of the image and what's going on here, and also, like I said, the relative scale of the different objects, right? So here's the popular Rho Ophiuchi area with, you know, just that beautiful, colorful area of the night sky. Here's the Lagoon Nebula. The Swan and the Eagle are up here. If you're in the southern hemisphere, you're familiar with bright targets like the Cat's Paw, the Lobster Nebula there. Here's the Pipe, sort of a series of dark nebula, nebulae right here that form a pipe shape. This guy up here, infrequently imaged because it's about 10 degrees across. This is the Zeta Ophiuchi Nebula. It's a very old H2 region. But just to give you a sense of, you know, what's at the core of our galaxy. Another popular area that people image, of course, everybody's favorite here in the Northern Hemisphere, Orion, right? Here's a look at Orion in this mosaic, just sort of zooming in a little bit. Of course, M42 and the Horsehead. Here's the Rosette, and then the Monoceros Loop that goes all the way up to the Foxfir and Christmas tree area over here. And then you got the Lambda Orionis ring up here, another huge one. So you see a lot more images, to be fair, of the Lambda Orionis ring these days, but it really requires like a telephoto lens, right? That thing's, you know, a good 5 or 6 degrees across, I think. When you look at the sky at this scale, you just sort of see different things, and you see a lot of big nebulae pop out that you wouldn't normally notice. I love, by the way, the color contrast Betelgeuse and Rigel down here, like this sort of blue gold color. Again, you know, really stands out in photos. And then while we're just sort of looking around at the different areas of the sky and looking at popular areas to image, let's look up here where the Pleiades are, right? So, you know, if you're looking at them in individual images, you might forget sort of how close the Pleiades are to the California Nebula over here, and also over to Auriga, right? So here's the Flaming Star Nebula, tadpoles, IC 405 and 410 over here. You got the Hyades, plainly apparent down here with the bright yellow Aldebaran star there. So, you know, this patch of sky really has a lot a lot going on in one small area. If you look at the image, you'll also see some other large objects here. These are ones that are seen in images even less frequently. So this guy down at the bottom, this is called GUM 35. This is actually cataloged as one giant object, and it's just a huge emission nebula. I can't even remember. It's like 30 degrees or something across. It's just absolutely gigantic in the southern hemisphere. And then even less frequently seen than that is what's called the Fishhook Nebula over here to the right. This is Sharpless 245. Really faint, really old emission nebula over here. Again, not imaged because it's just, you almost require like a 50mm lens to capture it. But it just, you know, gives you a sense of the scale of things and reveals some very large objects that you wouldn't normally look at. Okay, so how did we acquire this image? Or how did we put this whole thing together? So like I said, this took about 2 years. And the first part was actually planning the image. It's not normally a mosaic. Yes, you can plan it out in Nina or your favorite astrophotography software, or even manually plot it out. But it does require a little bit of special planning to plan out the entire celestial sphere. So I'll go through that. And then I'll talk about what we use to acquire it. We use some pretty basic equipment to do this. And then the processing, which was actually about 6 months of processing. This was about 18 months to acquire the data. It was about a month to plan it, about 18 months to acquire it, and about 6 months worth of processing. So planning. I'm going to throw this question out there. So if people want to type their answers into the chat. What's the largest number of panels that you've ever combined into a mosaic? I know a lot of people have never tried a mosaic. They can be a little bit intimidating, but once you try one and you get the satisfaction of getting that nice wide field with even just 2 panels put side by side, it's kind of addictive. You're like, oh, I want to go bigger. And then you try 4, and then maybe you try, a 6 or an 8 panel mosaic. So if you're interested, just type into the chat what the most panels you've ever combined into a mosaic was. This, while you guys are typing that in, this image
Charles,
is 150.
we have some, I guess the delay has been less.
Oh, okay, great. Already answers, huh?
Well, I've got a bunch of answers. Let me just read them off.
Yeah. What are some of the numbers we're seeing there? I'm just going to.
Brad said 2. Wolf Bobolan, if I got that pronounced right, is 8. John said 4. Linda Thomas said 2. Chris said 6. Al said, smart aleck answer, 1. Of course.
Clever.
GB Ray said 2. Brandon 2. Gary said 2. My gosh, this goes on and on. Steve says 12. Marcel said 6.
12's pretty impressive.
Gowie says 4. Norman says 0. I'm sorry, we got to read everyone's answer off. Sorry. And that's all it for now.
All right.
I personally once did a 24.
24. Wow, that's yeah. And you can vouch then for the processing difficulties of a large mosaic then, huh?
I vowed never to do that again.
Yes. Well, it's a bit like telescopes. It's easy to start with 1 and then you got to have 2 and then, oh, now you got to have 4. But then you're right. At some point you reach madness if you have 24. And it just starts to get to be a lot of trouble. So this one, this was 153. That's how many panels it took to basically to cover the whole sky with the field of view and the sensor that we have, which I'll go over in a little bit, and ensure that there was adequate overlap between all the panels. You can't just do this in, and this, probably obvious to a lot of the viewers, but you can't just do this from one hemisphere, right? To see the whole sky, you got to have at least one site in the northern hemisphere and one site in the southern hemisphere. And so we did that. We ended up with 3 sites to maximize our imaging time. But you have to be able to have Australia or Chile or any of the popular imaging sites in the southern hemisphere, and then one in the north. So that solves the question of where to point the camera. But the other question was when to take the pictures to optimize this. So I also wrote some software to not only plot this, but to figure out where or what times we should take the pictures, what dates at each site. So you can see here we'd originally planned for a site in the UK, Chile, Spain, and the US. We actually dropped the US. This was my backyard. It was too cloudy, and it just ended up not being worth it. I ended up not contributing enough data to it. So we just stuck with the 3 sites that we had, mostly Chile and Spain, because that's where we were getting like 250 to 300 dark nights a year. But if you think about it, we see different parts of the celestial sphere at different times of year. And the very simple reason for that, again, to put it in a very simple schematic here, is this is the explanation, for instance, for why we call spring galaxy season, right? So when the Earth is on this side of the sun, and let's say this is the part of the orbit where it's spring, right? The nighttime sky is looking away from the sun, and that's also looking away from the center of the Milky Way, right? So that means you're looking out of our galaxy, out toward other galaxies. And then on the other side, when it's autumn, the nighttime sky is centered more closely on the center of the Milky Way. So you're looking into our own galaxy, and you're seeing a lot more nebulae, for instance. But to see all of it, to see into our toward the center of our Milky Way and everything outside, you're going to have to space your images out over the course of at least 9 months, if not more. And in our case, like just for practical purposes, it took about 18 months to take all the pictures. So what did we use to take the pictures? Well, our initial setup looked something like this. We ended up simplifying this dramatically, but this was just, I'll leave this up here just as an example of what turned out not to do. So you see here, this was our main camera. So this is a ZWO 1600 monochrome camera, very, very common, with a micro four thirds size sensor. This was before the 2600 series had come out. If I could do this over again, sure would have been nice to do it with the 2600 and the larger APS sensor. It would have had fewer panels, but this was what we had at the time, and this is what we started with and stuck with. Here's the filter wheel. This is the lens that we used. This was the manual focus Samyang or Rokinon, depending on where you buy it, 35 millimeter. It's an f1.4. We stopped it down to f2. This is very sharp. I'm a big fan of these Rokinon Samyang lenses. I use the 135 as well. Stop them down half a stop or a full stop. They're incredibly sharp, and you still are shooting at f2 or f2.8. The problem is their manual focus, so you have to somehow find a way to focus them. This was an abandoned approach, so we started. So this is a flea atlas focuser. So this is the definition of overkill. This is a focuser that will handle. I don't even know how many pounds of weight this thing will move, but it does not work, by the way, to try to move the lens in and out. The telephoto lenses are not like simple telescopes. The lenses move relative to each other inside the lens to focus. It's not a simple distance measure. So this was the first attempt that we had that didn't work, but we did find a way later. This was the first site. This is Max's backyard, garden as they call them in the UK. This was in Northumberland in the UK, and you can see he's on Holy Island there. So there's like the ruins of it's literally like a ruins of a castle. It's pretty magical there in the background. But he's got really dark skies. So when it's clear, he's like looking out over the North Sea, and so he's got very, very dark skies. So we were able to capture a good number of subexposures there. And this also allowed us to test the equipment, get things working before we went remote. Site number 2, and the most productive site, this is Chile. So this is deep sky Chile, in the middle of, I don't know if it's quite in the Atacama Desert, but it's the middle of the desert for sure. This is Frank Jobard. This is he's the proprietor there. You can see our imaging setup there. This is the drive to get to it. And they tell me that the Vera Rubin telescope is being built somewhere out here on the horizon. But as you can see, this is not a rainy location. This is not a cloudy location. You get a lot of dark, clear nights here. And there is no light pollution at all. So this is the place to go to image those really difficult broadband targets, the dark nebulae and things like that. This is Max took this picture. Max is the one who put the telescope out there. I didn't actually get to go to Chile, although I'd love to visit sometime. This is some sort of these cactus seed pods, apparently, that are easy to spot during the day, but he said we're really slowing the drive down on the drive back at night because these spikes are about 6 inches long and will go right through a truck's tires. So you have to make sure that you don't hit any of those on your drive in and out of there. Our third spot was Spain. So this was at EI, a remote hosting facility in Spain. And here you can see the final setup that we used. So I mentioned that the Flea Atlas focuser was a mistake. The proper way to do this is shown here, which is to actually put a gear or some sort of belt onto the lens and focus it that way with the stepper motor. So a little bit more trimmed down, lighter, and worked great. So this was our final setup that we deployed both in Chile, Spain, and the UK. And you can see how dark the skies are. There's really beautiful Milky Way. Okay, so one thing I will note is the back focus on most of these lenses does not provide enough distance for you to put in a filter wheel. And so in this case, you can, but you end up with your infinity focus all the way out at the very, very limit of focus. And to create a proper V curve in your autofocus routine, you have to go past focus, right? So Max actually had to take these lenses apart and remove a couple of millimeters out of the back of them and then have them reattached. And that allowed us to move infinity focus on as far as the rotation of the lens off of infinity and closer to this 10-meter mark. And that allowed us to create a proper V curve for focusing. So this is one watch out when using these manual focus lenses. You have to make sure you've got enough back focus space there. And you may have to do manual modifications to the lenses sometimes. And then this is what it looked like as the data started coming in. So we use Nina. I'm a huge fan of Nina. This allowed us to automate the imaging. So I created the center coordinates for all those panels. And then we were able to just upload those right into Nina as a sequence, and then off the imaging we went. I think we targeted So we took 6 channels, so RGB, sulfur, hydrogen, and oxygen. We shot for about 1 hour per channel, per panel. And this is at f2. So 1 hour doesn't sound like a lot, but for those of you, who've used these fast lenses, when you're shooting at f2, that's actually a fair amount of data. And actually, you can even you can blow out the highlights on something like M42 if you're not careful. So we were able to achieve this goal nearly an hour for every panel. So, but if you multiply that through 153 panels times 6 channels times an hour per channel, and then with reshoots and things like that, we shot about 700 hours total exposure time here. Okay, so the data are coming in. The hard drives are filling up. And then I'm faced with the daunting task of starting to process this. So once we had most of the data in, I started the ordeal here of processing. And I just want to talk about when you're taking a mosaic, that brings complexities on its own, but then a full sphere mosaic actually brings some additional complexities that we'll have to talk about a little bit. So one is just the sheer size of it. Like I said, the final image was a billion pixels. The Photoshop, for instance, I wanted to just rearrange things a little bit in Photoshop, and I wanted to create those layers that you saw before where I could sort of label the constellations and things like that. Photoshop, kind of fails if you try to go over 64,000 pixels wide for an image, right? So that it does impose some limits there. Thankfully, that was approximately the resolution that we were shooting at, but I definitely had to upgrade the processor on my computer to do all the processing. Had to upgrade the memory as well. So just a big project in terms of compute that was needed. The other thing, and for those of you who had done mosaics, you know this, that the difficulty of mosaics mostly comes in dealing with gradients. Like, you have to make sure your gradients are just really processed out well, because if you don't, you end up with, you see the seams, right? Or you see, sort of a gradient from one side to the other. But the worst is when you see the seams, and that you really want to make that seamless, and you have to match the brightness in each panel to do that. Well, when you're at this scale, the seams are one issue, but then even just gradients between groups of panels becomes another thing. So we had to figure out some ways to deal with that. And then the final thing is that the full sphere doesn't have a boundary, right? So the surface of a sphere, or just inside, like the celestial sphere around us, there's no edge, right? So it's like going entering a room through one door and exiting out one and then coming back in. We're like Pac-Man, where you go off one edge and you come around the other. Like, it has to overlap, and the processing software does not deal with that sort of boundaryless condition very well, let's say. So we had some issues there. So this is just an example. So this was what my summer project this year was. This is a 20-panel mosaic. And this is bounded, right? So I could literally go into Nina and in 5 minutes enter in what the parameters of my system. It would load up a deep sky survey image and overlay it and let me plan it out. Of course, executing it, right, took all summer, especially with like I said, the few clear nights we get here in Pennsylvania. I think this was like 25 nights or something of data, and then processing it was a burden. So, but at least it was bounded, and at least you didn't have to deal with anything wrapping around or different sites. The processing flow for the boundless mosaic was a little different. So the first thing I'll say is, if you're doing a large mosaic, there's a great tool in PixInsight called Catalog Star Generator, and this is the way to go for really big mosaics, because what it allows you to do is generate a fake image of stars. So it just plots stars. So, it uses the Gaia or Hipparcos data, and it just plots stars, and then you create a foundation image that you can then take your mosaic panels and paste them onto. And that way, you don't have to worry about correcting, or you have to correct the distortion, but you don't have any residual errors from distortion at the edges of your pictures where they overlap. where the field isn't just perfectly flat, it's hard to register those like imagine like bent fields trying to match those. You just match everything to what you know is a very flat field because it's completely artificial. So for this project, I created a massive 32,000 by 16,000 pixel foundation image, and we're going to use that to register everything to it. Again, talking about the limitations, when dealing with a mosaic this big, I'll just say like Catalog Star Generator would do 16,000 by 16,000, right? It would do, or I think it was 16,000 by 16,000. And then I had to do that twice, to create the whole sky. So, just reaching the limits of what you could do as far as image size. Of course, there's integrating all the data that's coming in for each panel, right? But then we had to reproject it. And I'll show you, so we've chosen an equirectangular projection. You can always reproject it later, but we wanted to get everything in place there. So there's great tools, believe it or not, in PixInsight also. PixInsight seems to have everything, if you look deep enough into it, that allow you to actually reproject your images to whatever projection you want. Once we've done that, we can't just go straight to laying down 153 panels at once. It's unmanageable. So I built these, like what I call super panels of just 5 to 10 panels to make it a manageable problem to solve, to get rid of all the gradients, get rid of any seams, things like that. And you can see here, so this is where we're reprojecting with mosaic by coordinates. Gradient merge mosaics, is the main mosaic tool in PixInsight to actually merge the mosaics together. And then I did have to write just a little bit of light code in PixInsight because there's not a good tool for matching the median brightness of different panels, to doing what's called linear fitting of super panels to each other. Then finally, we can kind of go back to step one, take those super panels, and we're going to align them to that master foundation image. And then once that's done, then I've got the actual normal post-processing stuff, right? So this is where you're, combining your color channels and you're increasing saturation and, curves and levels and all that good stuff. So let's go through a little bit of that. So this is like a very zoomed in detail of that foundation image. So this is Catalog Star Generator's output. You probably recognize this cluster of stars, either if you happen to know, of course, this is the Pleiades, but this is also, if it looks like the Subaru logo, right? Because Subaru is the Japanese term for the Pleiades. But you can see that this looks like a mediocre image of the night sky, but it's really just a synthetic image. And NASA actually did something very similar to this. If you were to take all the stars, and again, I can't remember, I think this is the Hipparcos data, and plot them, you will actually generate an image like this. And NASA did exactly that. And it creates this very cool looking sort of, pseudo Milky Way image. But you'll notice like all the nebulae are completely missing. M31, the Andromeda Galaxy, would normally be right here, missing, because this is just a plot. It's not actually an image. All right, and I'll just throw out another question to type into the chat. It sounds like we're getting pretty good responses, so I'd love to hear what's the primary or favorite image processing program that you're using right now. You've heard me talk a lot about PixInsight, but I'd love to hear what other people are using. And I don't want to start a war. People are pretty partial to their favorite tool.
Good luck.
While we're waiting for those responses to pour in, Eric, have you been monitoring? Are there any questions that Charles might want to
Yes. We're getting some answers. Why don't we give them a moment to put in the answers?
Yeah, let's give them a moment to answer. Meanwhile, we'll catch up on some questions that have come up.
So, Al, actually, you answered this one. What method to project on a sphere? And I think you've answered that with the artificial star generator, which, by the way, I'm marking that down because I would like to experiment with that. How big was your data set?
Goodness. We were also taking all the other images of the individual objects. So, right, when we were creating the book, we were creating this big image, but this is just one image in the book. We were also taking images of each 110 objects. It was 5 terabytes by the end. My guess is that maybe a third of that was for this one image. So probably between 1 and 2 terabytes of data.
Another question, how much did your rig weigh, the final rig?
Oh, it was pretty light actually. So it was the 35 millimeter lens, and of course, you know, all the dovetails and things like that. It had a power supply on it. I don't think it exceeded more than 10 pounds or so. And actually, we were able to sort of assemble it and box it up and actually ship it safely to Chile in like an air case.
So, okay, we're getting some answers in. Let me just read them off. Of course, you know the primary answer is going to be PixInsight. But
All right.
so I'm just going to read down because no sense in putting it. PixInsight TE, PixInsight, PixInsight APP, PixInsight, 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 sorry, MS Paint, CCD Stack, PixInsight, 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 GIMP.
GIMP, yep.
And, oh no, that's a comment. APP for mosaics, PixInsight for normal.
What
And
was? Oh,
I think that's everything.
Okay.
what is TE?
I don't know.
Hey, whoever typed in TE, could you? I'd go back and check, I guess. Could you tell us what TE is?
I don't know what T is.
Yeah,
Yeah, who's that? Visible dark.
Visible dark.
Yeah, visible dark. Tell us. Oh, here's a Cyril just got added. I
Cyril.
was counting them up. There were 9 PIs, a TE, a GIMP, and a couple of AAPs, but I'm not sure I've got that accurate.
Great. And that's
Visible
it's
dark.
amazing how
And
that
there are 70 people watching right now, so we've got some people who are typing in. So
yeah,
like myself.
I mean, don't forget the MS Paint because that is super impressive.
And Photoshop.
Yay, photo. So that's what I was gonna say is that it's amazing. So when I went to the Northeast Astro Imaging Conference in 2012, it was nearly 100% Photoshop, and there was some Maxim DL I think in there and stuff. And PixInsight was like this up and comer, right? 10 years ago, and now it's dominated. And I will say, at least for the purposes of what we did, like there's some deep processes in there that maybe aren't used that much, like mosaic by coordinates, catalog star generator. You know, they're not well documented, but there's a lot of great stuff in there that you just don't find pretty common.
I see Star Tools is in here.
Oh, good. Star Tools, yep.
Star Tools, and I think that's it.
Okay.
Of course, I think a lot of people are using combinations of PixInsight, Photoshop, and
Yep.
Yeah, somebody pointed out that it's is it what's your favorite or which ones do you use?
That's true. Yeah, it's more like I was kind of expecting a lot of people to put. Yeah, maybe I should have put which ones do you use? Yeah, so I think you're right. I think most people use multiple programs.
Let's credit that word's due. Luftbubblen. Okay.
Did we find out what TE is?
Yeah, it was a goof.
yeah,
Somebody
mistype.
He had us all thinking that there was this awesome new image processing program we needed to look into.
It's visible dark secret programming.
Yeah,
That's how he gets those great images.
Okay.
All right, so just to give you an example, now this is one of the nicest looking ones, but some of the individual panels were just fabulous on their own, right? So this, of course, is the H alpha panel centered just north of the northern part of Orion, and you can see the Lambda Orionis ring there and part of Barnard's loop. So yeah, some of the individual panels were great, just right out of basic processing. To my prior question, we actually used AstroPixel Processor, APP, for all of the pre-processing and the basic processing of each of the panels. And then to assemble the panels into the mosaic was all done in PixInsight. So this is sort of a two program process. This is how I got to the super panels. So this isn't taking it all the way, but if you can imagine, for each of these quote unquote super panels, which is like 5 to 10 individual panels, you've got the 1 hour of subs that came in. You got to integrate those in AstroPixel processor, of course, calibrate and everything like that. Crop out any fringes. We did gradient removal there. Then they went into PixInsight where we plate solved them. Then they got very slightly rescaled because we had to match that foundation image, and the image scale was off by like 11% versus our image scale in the sky, and so we had to just rescale them slightly, and then use mosaic by coordinates to basically put them into a certain area that was shared by 5 or 10 of the other panels. So you sort of repeat that for that whole process for, let's say 5 or 10 panels. This is just for one channel, by the way. You take those, then you have to linear fit each of these to each other, right? So they're going to have slightly different background brightnesses. So you have to linear fit each of the panels, and then use gradient merge mosaic to merge them into one, what we'll call super panel. So this is like a chunk of the sky. So you have to repeat this for 153 panels, all the subs you've got, times four different channels. In this case, actually, I will say, I said at the beginning, we took RGB and then we took hydrogen, sulfur, and oxygen. We ended up not processing the sulfur and oxygen. There just wasn't enough there. We have the data, but it wasn't adding that much to the image. So we kind of left that to the side and stuck with just hydrogen alpha and RGB. So this is what an image, one panel looks like. So I mentioned that mosaic by coordinates can do this cool thing where it can reproject. Once you've plate solved it, it can reproject your image into any projection you want. And it's not something you would normally do, to be fair, in astrophotography. You're not usually interested in reprojecting. When I say projection, I'm talking about map projection. So you've heard of typically the one everybody knows about is the Mercator projection of a map. But there's, this equirectangular, there's Malvide, there's all these different other projections. And you'll notice you've seen probably the cosmic microwave background radiation images with the the big wide oval like that. I think those are done like in a Malvide projection. But this is what it looks like, and it's pretty cool. It sort of handles all this for you in mosaic by coordinates, which again I think is a pretty powerful tool. This is what one of the super panels looks like. So now we've taken like 6 of these individual panels, and we've in this case actually done it for all RGB color channels, and we've corrected the we've trimmed them, and we've linear fit them, and now we run them into mosaic by coordinates just to reproject, and then finally we gradient merge mosaic to overlay them all together. And this is one of the first ones we put together. Pretty seamless. I mean, it was looking pretty good, so I was pretty pleased with this. This is just one of the first ones that came out, and you can zoom in and sort of see what kind of resolution we're getting. The actual ultimate resolution here was 20 arc seconds per pixel. So remember, we're dealing with a 35mm lens, and yeah, 20 arc seconds per pixel for the whole sky is pretty good. I showed this one because we talked about distortion and projections. So this is what it looks like when you get close to the pole. So you've got getting up north here, you can see how the stars start to stretch out just as a natural function of the distortion of the projection. One thing I didn't think about when I started planning this thing was that these stars, for instance, when you try to have them register to the foundation image, won't register because PixInsight doesn't see them as stars. They're big long streaks. So I had to make sure that each one of these super panels had a couple of anchor panels down at the bottom where the stars had no distortion, and those would register and sort of hold the top so that it was put in the correct place, because these PixInsight couldn't figure out that these were stars, which makes sense. This was just me. I'd love to say there was some deep algorithmic truth that underlies how I put the super panels together, but it was literally me just working through them and going, yep, okay, these 6 look like they'll fit together, and then sort of circling them as I completed them. So this is just the notes on my desk about 2 months into this, is I was like, okay, I got these done, which ones go into the next one? Very manual, this part of it.
There's a question here.
Yeah.
I thought you might want to answer. I'm pretty sure it comes from Tim. Did you try the photometric mosaic function in PI?
Ah, yes. So photometric mosaic, number one, did not exist at the time. And number two, photometric mosaic is very well set up for anybody who's used it for perfectly grid aligned panels. And it's particularly good for just matching two at a time. I will say it is the perfect way to match panels. I agree. I think it is the optimal way to build a mosaic because what it does, it actually knows the brightness of the stars, and it can sort of use the brightness of the stars to figure out how to automatically linear fit your panels together. It is an incredible solution. It is too burdensome at this point to use for like 153 panel mosaic. Like I don't think I could have done. I would have had to basically done it one panel at a time. I'm convinced that if I had put in the time and done it one panel at a time, it probably would have been perfectly gradient free and it would have just been amazing. But yeah, it actually didn't exist when we started this. But great question and great tool. So this was another of the first panels that came out, and I just wanted to like make sure that the projection was working, right? Because you can't have any errors where you've got sort of, you know, stars misaligned. It won't look good in the final thing, obviously. So I took that image from NASA and I took one of the first super panels that we had and I just put it in Photoshop and I put it like 50% transparency. And gosh darn it, it lined up. The stars were just pixel perfect. I was so excited. So the tools, the mosaic by coordinates, everything had perfectly reprojected everything. Once we figured out the right settings, I will say, to exactly where they needed to be. So this was fantastic. Okay, so now you got super panels. So now I've got 28 chunks of the sky. So this is where I had this was some light coding just to write a little bit of code to allow me to linear fit these super panels to each other. There is also something that I learned. If anybody goes through this again, you won't see it, but the gradient merge mosaic will actually create these very, very faint artifacts that spin out into the perfect black here at a level not 0 perfect black, but of like 1, 2, or 3 on like a 65, 0 to 65,000 16-bit scale. And I didn't know they were there, and they were causing all sorts of headaches until I finally figured out that something about that code creates these weird loopy artifacts that generate out here. So we had to clip the black point to get rid of all of those. That was, again, like a detour that took a week to debug that. And then the final thing that had to happen was anytime a super panel went over the right ascension 0, 24 line or over the top of the pole or bottom of the south pole, we had to actually trim the panels very precisely, because if it goes over any of those boundaries, you're creating a pixel now that has either a right ascension or declination value that's way different, right? So when you go over the pole, you might go from a right ascension value of 6 hours, you're going over to 18 hours when you cross over. Well, then the software thinks that it needs to do something that's like 24 hours of right ascension wide, and it just crashes. It just falls apart. So actually we had to go in and just very carefully trim all of these things. But once we figured out some of these challenges, just minor limitations of the software, we were able to start putting it together. So what did we get when the first time we threw everything together? Well, not bad, I'll say. So I was thrilled to see this when, as we were starting to put it together. So this is where, just showing behind the scenes here. Oh, look at that down in the lower left. We're going to need a reshoot for that panel. Like we must have, I either miscalculated or the camera pointed a little bit off or something went wrong. We have a hole here. I'll also say we've got these guys here, which is another thing that I completely didn't think about. But this is Jupiter and Saturn. And the challenge with those is that we shot the different channels on different nights. And so you ended up with Jupiter and Saturn moving between frames and then, or between nights. And you ended up, if you zoom in, you'd see like they were kind of in different spots. So I actually had to go in and sort of manually crop those out and pull data from another night to sort of fill in where Jupiter and Saturn were. Okay, so this is progress. We're almost there. We're in the home stretch. I hope you're feeling as relieved as I was after like 6 months of processing this. It feels like the end is in sight. And this is the RGB image. So once you get all the RGB panels processed, this was the final result here, which I was absolutely thrilled with. Love seeing, you know, the rich color of the central Milky Way. You can see some of the nebulosity, especially the bright nebulae that we all shoot. This is, you know, I was really thrilled. When the H alpha data came together, though, this is actually my favorite image of the whole thing, which is this one. So the universe in hydrogen, an ionized hydrogen, if you will. And this is where you really see the, you know, some of the stuff we talked about before, the Fishhook Nebula, Gum 35, things you just don't normally see that much. But this is like just the nebula view of the galaxy. I absolutely love this image. Just to orient you a little bit, here's the North American Nebula, and here are the veils, eastern, western veils, right? Here's IC 1396, Heart and Soul Nebula, California, but it's all there. And if you zoom in, you can, you know, sort of see all of these in their glory. But then
we ask another couple of questions.
Yeah, please throw them out there.
The questions are coming in. Someone was curious. Tim was curious. What kind of computer did you use? What are the specs?
Great question. Nothing super powerful. Is a Ryzen 7. I ended up upgrading my RAM to 64 gigabytes, but in the end, I think probably that might have been overkill. I probably could have done with 32 gigabytes. So yeah, not like a super special computer.
And how did you add in the hydrogen data to the RGB?
Ah, great question. So this is this is something we typically would do in PixInsight, and I would use a combination of tools, but I ended up adding it both to the luminance and to the color. So it's mostly to enhance the red channel, but also adding it to the luminance channel as well. The way to do this in Photoshop is actually the easiest thing, and that's where I actually had the best color, was to add it as a layer and then adjust it to the red color that we want, so that almost magenta red of ionized hydrogen, and then overlay that as a partial layer onto the RGB data. So I actually did that in Photoshop, and so it's a combination of color and luminance added. And that's a great segue. I'll show you what that looks like. So this was the hydrogen alpha RGB image. So were there other questions coming in that you wanted me to answer?
Not right now.
Okay. So this is it. So we're back to the final image. So this is after all of that, after cleaning up little seams, reshooting a couple places, adding in the hydrogen alpha on top of the RGB. I think this was the right way to go. Instead of trying to bring in the sulfur and oxygen as a separate narrowband image, we decided this was just the best looking approach for the whole thing. So just to orient you, this might help a little bit. It's easy to get lost when you're just looking at all those stars. So then I created overlays that I could put into Photoshop and overlay things on. But here you can see the different constellations. So maybe this helps orient people to sort of see, okay, here's Cygnus, right? There's the summer swan, and you can see, like we said, North American Nebula up here. Here's Cepheus, Big Dipper, you can't miss it, but Boötes and Arcturus right here in the middle of the spring sky. Really just sort of gives you a sense of where things are, and again, like what the scale of everything up there is. All right, so you might look at that image and say, oh, that's great that you've got this big sky image, but the stars are all distorted at the top. But one thing we did actually in the book was we used these to orient people, and I reprojected again, which again, I said that, mosaic by coordinates is a very cool tool to be able to do this. So we could reproject it to, I think this is like a gnomic projection or like stereoscopic or gnomic, but a more normal view of like, looking at a section of the sky when you don't have to show the whole thing, when you only have to show a part of it. You can reproject it. And so this is what we use in the book, like kind of like as chapter headers, basically. So we took the same data, took the H alpha, and again, you can see Cygnus, and here's Lyra, and it gives you a much better sense of like the 3D nature of things when you reproject it like this. And that's it. So I will just say, the book is out. That was what this image was created for, was the visible universe. It's quite expensive. It will say the economics of printing books are not very good. So it's $75 on Amazon. For like the next month, if anybody wants to buy a copy, we can sell them in the US for $65, including shipping. If you want me to sign it or write anything in it, we're happy to do that, or happy to keep it clean. And you can email me here at deepskyprimer@gmail.com if you're in the US, or you can talk to Max in the UK, and he can ship them to Europe and the rest of the world. That's the cheapest place to do it. But that's what this image was created for, was just to provide some context for the objects that were in this book, which came out this spring. So if anybody's interested, you can go to thevisibleuniverse.com. All right, any other questions?
Actually, I think about half our audience is having angina thinking about the scope of this. I know I'm having palpitations. Like,
Charles,
how many?
we did. Oh, go ahead.
How many times did you? I want to say seriously or casually think about giving up?
A lot. I will say there were times where I thought that we were never going to get the whole image together, and my backup plan was just to process big chunks of it and like throw them in the book as like, here's a big chunk here, here's a big chunk there. Really, it was figuring out the exact parameters necessary. There were sort of some, wasn't well documented how to choose the parameters for some of the things in like mosaic by coordinates. But I guess what committed me to it was the fact that we had all the data at that point. So we'd kind of already shot all the data, and I really, really felt the pressure to like deliver on getting it all finished.
Do you have any idea how many hours you put in on this project?
I don't. I mean, it was kind of a weekend project for the nights and weekends it was about 6 months really to get the processing. There were, like you said, a couple of moments where it was kind of a full stop and I was just pulling my hair out trying to figure out what to do. But then once we got the process figured out, then it was, I mean, I don't want to say it was easy. It was, at some point, once I had the process done, it was just really tedious, right? Like going through 153 panels times 4 channels. Once I had the process done, it felt like victory. But then I had this, weeks of work ahead of me of just grinding through all the processing and making sure that it looked good. So I don't know how many hours, but probably 10 hours a week for something like 25 weeks or so. So yeah, probably 250, I would guess.
I don't see any more questions.
Well,
Alex?
yeah, I do see something, and I don't about the all sky cam.
Yeah.
What's the difference between this picture and an all sky cam picture?
Well, so like a little all sky, like super wide angle fisheye lens type thing, I'm guessing they're talking about.
I have no idea what
I think that's what they're talking about.
Yeah. So to the earlier point that so one big thing is that's all of the sky that you can see at the time of year that you're at and at the location you're at, right? So yes, you can take a full 180-degree image and you can do that from one location on Earth at one time. And that would allow you to capture, maybe 1/8 or 1/4 of the total visible universe out there. But it's also going to do it at a much reduced resolution, right? So you're taking a 180-degree field of view and you're putting it on, whatever at most, the I don't know, 60 megapixels. Let's say even put a giant chip on there. Most of those cameras are actually teeny tiny. So yes, you could sort of do something similar, but it wouldn't be at nearly the same resolution as what we did here.
Now, having read your book or having looked through your book, I know that you do have a description of the mosaic and all that other stuff, but you've also got 3 tons of pretty pictures in there. And tell us about if I wanted to say, well, what am I going to image tonight, which is what I use the book for.
Yeah.
Tell us what happens with that book.
Yeah, so they're grouped by season and sort of northern hemisphere, southern hemisphere. So I didn't have any good images of that, but you can sort of see the table of contents here, and like it's like here's in 3. That's like northern hemisphere winter approximately, and that would be where you would look to find what might be out. The other thing is we put the full image data for every single image into an appendix. So every image in the book, you can see exactly what equipment was used, how long each exposure was, the total time, everything about it. So you can go, oh, crap, if I want to image that thing, that's going to take 25 hours of imaging time. Maybe that's not the one to do tonight. The other thing we did was these charts, which show, we're just calling it imaging hours. And what this is this is the number of hours at a given latitude for every day of the year that the object is above 30 degrees, right? Typically, you don't want to, you lose a lot of quality when you get below 30 degrees of altitude. You get too close to the horizon. So we just calculated at, 30, 40, and 50 degrees north and then 30 degrees south latitude, what the, how much time you can expect to get good imaging time on that object. And that might help you also go, you know what, it's okay tonight, but this thing, I can get 12 hours a night on this object. If I just wait until December, maybe I should pick a different target for tonight.
And these images that you're using as examples of the ones that we're seeing right now, those were not taken with the system that you described to take the mosaic.
Correct. Yeah. So we also set up in Chile and Spain, of course, my backyard here in Pennsylvania, Max's garden in the UK. We use mostly a Takahashi TOA 130, a FSQ 106, the Samyang 135 lens, and a couple other targets, Astrotech 8RC and a couple others. There's like basically 6 scopes that we used for the whole thing. So these are proper, regular, deep sky images taken with full-size telescopes.
Okay, thank you.
Yeah.
I've got a question for you. Could you talk a little bit more about what you did, how you managed the planets, Jupiter and Saturn, as they moved around?
Yeah, it's one of those things like, wow, I really should have thought of that when I was planning this thing, but I didn't until I noticed them in the final result. I was like, oh, I got to figure something out with that. So what I actually ended up doing was, because we'd taken the exposures on different nights through different filters in most cases, I was able to go in and fudge it a little bit and say, okay, well, Jupiter was here. I'm going to cut it out of, let's say, the green and blue channels, which were taken on this night. And I'm actually going to plug in the stars from the HA data, which was taken 3 weeks later. And, it's, if you're zoomed in, you might notice, oh, those stars are actually kind of devoid of color, right? But you don't notice it in the big picture because it was just such a tiny little area of crop that I could do that I fixed it that way. But yeah, it was just sort of looking where it had moved and then finding data from another night that I could plug in underneath, once the planet had moved, basically.
You mentioned zoomed in. On a book, you really can't zoom in. So
yeah,
is there any opportunity to zoom into this image?
Yeah, so let's do that. And I can do it to some degree here. I will say what we're also doing with these data is creating a virtual reality app that wraps this around you. So that's kind of the next step with these data is moving it to you can look at it in a headset. Yeah, so I'm a little bit limited in how far I can zoom in here in PowerPoint this way, but at least it kind of gives you a little bit of a sense. There's the
what I was actually asking, was there any way we could zoom in on this online?
Ah, great question. So the only place I have this image posted, I have it posted on my blog. and that's at digitalstars.wordpress.com. That's the only place we've posted it online. I posted, I think it's an 8,000 by 4,000 pixel version on there. I think that's the one that we have up there. To be honest, it gets a little unmanageable because when you go one step up to like 16,000 by 8,000, it becomes a 100 megabyte JPEG file. So we've mostly just kept to, like the 25 megabyte range, which, sort of limits the resolution. So the short answer is, to a limited extent, on my blog, you can see it, digitalstars.wordpress.com, but not the full 64 by 32,000 pixel monster. It's just too big to deal with.
Oh, could you go ahead and reflash us the slide with the email address so that Barbara Harris, one of our favorites, can see it again?
Yeah. Yes, absolutely. Yeah. So you can go to thevisibleuniverse.com, or you can email me if you're in the US, deepskyprimer@gmail. And Max is at max@natureguides.com, and he's shipping the copies. He's got a basement full of books over there in the UK, and I've got a bunch of them here in the US that we can ship out directly to people. So you can just email us, and we'll send you a PayPal link.
Okie dokie, pokies. I think we got all the questions, right, Derek?
I think we do.
Okay.
All right.
Is there any?
A lot of fun, guys.
Oh. What was that?
I say that was a lot of fun. Thanks. Thanks for having me. I hope you. I hope I gave you a little bit of angina, but then everybody's calmed down by now.
And remember, Charles, you can hang around after everybody else has to go goodbye, which is another great advantage of presenting on the Astro Imaging channel. You can talk to Eric personally after all this is over. Okay, Tim, you're in charge, right? Go ahead and take us out, buddy.
Sir.